My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, International Physics Adda, and YouTube channel, Pretam Kumar, I'd like to welcome you all to our International Physics webinar. Today it's our 272nd International Physics webinar, and we have with us here to Dr. Bharat Ratra sir, Distinguished Professor, Department of Physics, Kansas State University, USA. So he has already connected with us. So I'd like to welcome our speaker. Sir, good morning to your part. And good to hear. So thanks for joining with us, sir. And it's honors and privilege, sir, to host you.
Thank you very much.
Yes, you're welcome, sir. So dear student and viewers, I think you will witnessing a very exciting lecture. And I think you have already come to know the title of this today's exciting lecture. And title is the Accelerating Expanding Universe, Dark Matter, Dark Energy, and the Einstein's Cosmological Constant. You can join with us directly using the link. I will send the link in the comment section, and you can also ask question by commenting. So please enjoy this lecture. Sir, it's your time. You can start your session.
Thank you. Thank you very much for the very kind introduction. So I'm a cosmologist, and I study the structure of the universe and how it changes in time, how it evolves. And it's a very, very exciting time to be doing this now, mostly because we've had very good telescopes, both on the ground and in space, and they can collect much more light because they have bigger mirrors, and they have much more sensitive detectors, the same kind of CCDs you have in your smartphones, but they're more sensitive and they're bigger. And so we're getting a lot of data, and this data is reinforcing two very, very interesting results. I mean, the first result that some of you are probably very familiar with is that when we look at what contributes to the cosmological energy budget at the present time, we find that we only understand about 5% of the composition, and that's the atoms and molecules. And 95% of the contribution to the energy budget at the present time is unknown. And that's really exciting because there's so many things to be understood about most of the matter and energy in the universe. And the other really interesting result is that these cosmological observations seem to be suggesting that either quantum mechanics or relativity, or perhaps even both of them, provide only incomplete descriptions of reality, and we need to modify one or both of them. And that's going to be a really profound result if it holds up, because quantum mechanics and relativity have governed the foundations of physics for more than a century now. So I just want to draw your attention to this website down here. It's a really interesting discussion and explanation of how global warming works, and we have a lot of problems with global warming. So if you're interested, you can learn more there. So I live in the center of the US, and that's in the state of Kansas, and it's mostly grasslands. And this is an area, this is a nature preserve that's about 15 minutes away from where I live. And these are American bison. And this is a very nice place to go for walks. So I want you to kind of think about how far you've hiked, maybe in your whole life. It's a little bit difficult to even think about hiking much more than maybe 100 kilometers. And maybe if you've gone backpacking and you've done that very, very often, you could probably have gone maybe 1,000 kilometers in your whole life. And that's sort of the limit to which humans can go on large distances. And if you think about the distance scales you can probe on really small distances, probably the finest thing you can feel with your fingers is your hair. And that's about 10 to the minus 4 meters in diameter typically. So there's a very small range of distances over which humans can directly probe with their senses. And I have a bunch of length scales up here. The units is in meters. And maybe you can walk 10 to the 5 meters, and maybe you can feel things as small as 10 to the minus 4 meters. But there's a lot of length scales that you cannot directly probe through any of your senses, both on very, very large scales and very, very small scales. And so the way you develop intuition on large scales and small scales is very different than the way you develop intuition on these scales. I mean, on these scales, you can do things like colliding balls together, and you'll figure out energy and momentum conservation and friction and Newton's laws of motion and things like that. But you cannot do that on scales much larger and much smaller, because you have to use instruments, either microscopes or particle accelerators, if you want to go down to really small scales. And on large scales, you have to use telescopes, and you collect the light and the photons and turn that into electrical signals that you process. And you don't get any direct feel for those things. So what you're going to do is you're going to convert those electrical signals to numbers and compare those numbers to predictions you make from mathematical models. And so on very large scales and very small scales, the way you develop intuition is to develop these mathematical models and compare them to measurements that are made indirectly. They're not directly something that you can touch with your human senses. And so the way you develop intuition is very, very different here. And so probably it's not that surprising that when you think about what governs things on very small scales, which is quantum mechanics, and on very large scales, which is relativity, because you have things moving at very high velocities, that they seem very strange. And that's because the way you develop intuition about these scales and these scales are very different than what you do on these scales. And often people don't realize how large a range of scales we have out here. So if you want to get good at science, it's kind of important to try to develop some mathematical skills, especially things like calculus. And I want to spend a little bit of time walking out from human length scales to much larger length scales, on which cosmology is the physics that we need to talk about. So I'll start here, and you probably recognize this person. So I'm going to use him as a typical length scale. I could also do this in terms of Einstein's mass or Einstein's age and talk about mass scales and length time scales, but we don't really have time. So what I'm going to do is I'm going to talk about an Einstein as a length scale. And in terms of units that you might be more familiar with, one Einstein is roughly 2 meters. And I'm going to jump from him to a picture like this, which has only become possible in the last 5 or 6 decades after we've launched satellites into space. And you can see here Africa and Madagascar and the part of the Indian Ocean on the Arabian seaside. And if you want to kind of get some idea of what this scale is compared to this scale, you can kind of think about how many Einsteins you need to get to put one on top of the other from the North Pole to the South Pole. And you'll need a lot. You'll need 6.5 million Einsteins, because the diameter of the Earth is 13 million miles, 13 million meters, sorry. So you go a factor of 10 million or so when you go from human scales to the scale of Earth. And Earth is just a small planet. It's not that unusual. We can look at our nearest neighbor star, which is the sun. And to get the sun in terms of, say, the Earth, you need to take 100 Earths and pile them up one on top of the other. Or you need 700, maybe 750 million Einsteins or so to pile one on top of the other to get the diameter of the sun. And we can go to even larger scales, which is the Earth-Sun distance. So the Earth approximately orbits the sun on an approximately circular orbit. And there's a bunch of units you can use to describe that length. I mean, if you do it in terms of meters, it's 1.5 into 10 to the 11 meters, or 150 billion meters. You can also use the standard astronomers unit, the planetary science unit, people who study the solar system, and that's the astronomical unit, and that's just defined to be the average radius of the Earth's orbit around the sun. Or you can use the fact that light travels at a constant speed in a vacuum. And in terms of the light travel speed, which is roughly 3 times 10 to the 8 meters per second, the light from the sun takes about 500 seconds to get to the Earth. So if you want to compare this to the size of the Earth's orbit around, to the size of the sun compared to the Earth's orbit around the sun, you'd have to take about 100 suns, because if we go back and look at the diameter of the sun, it's approximately 1.5 into 10 to the 9 meters, which is 1/100th of the Earth-Sun distance. So if you take 100 suns and pile them up in a line, you'll eventually reach the orbit of the Earth around the sun. And you can do this in terms of Einsteins, and I'll let you work out how many Einsteins you need to do that. But people who study the solar system do not use meters as the length unit. They use either astronomical units or the light travel time. And if we kind of think about what the light travel time is telling us, that's telling us that when you're looking at the sun, and you should not look at the sun without protection, otherwise you'll damage your retina and eventually you'll go blind. But when you look at the sun, the thing you're seeing from the sun are those photons that left the sun 500 seconds ago. And so you're not seeing the way the sun looks right now. You're seeing it as it looked 500 seconds in the past. So let's go out to even larger scales. And if you look at the nearest star to the sun, that's the star Proxima Centauri. And the distance between that star and the sun is here in meters. In terms of AUs, it's 200,000 AUs. And in terms of light travel times, it's 4 years. So people who study collections of stars don't want to even use the AU as the length unit anymore, because you're starting to get many, many powers of 10. And they use another length unit, which for historical reasons is somewhat unusual. So if you look at this picture, you can see what that length unit is. That length unit is the parsec, and the abbreviation for that is PC. So what you have is the Earth going around the sun, and you take your observer and ask her to go way, way, way far away, so far away that this 1 AU over here subtends an angle of 1 arcsecond at the observer. And 1 arcsecond is a very, very tiny angle. So if you go around a whole circle, you have 360 degrees. And each of those degrees you can split into 60 arc minutes, and each arc minute you can split into 1 arcsecond. So 1 arcsecond is a tiny angle, and to get such a large distance to subtend such a tiny angle, you have to go very, 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 very far away. And that distance is defined to be a parsec when this side of the triangle is 1 AU and this angle is 1 arcsecond. And a parsec is an abbreviation for a parallax of an arcsecond. So if you're talking to a physicist, they would much prefer to use light travel time, seconds or years. And so it's useful to know the conversion from a parsec to light years, or you don't even have to say light years, you can just say years, and it's kind of understood that that's the time you're talking about, that it takes light to travel in a vacuum. So it's 3¼ light years, or 3¼ years for light to cover a distance of 1 parsec. And just to relate this to scales of humans and technology, I mean, the furthest humans have gone is the moon, and the moon is about 4 times 10 to the 8 meters away from the Earth, typically. So that's like 1 and maybe 1 1/3 of a second away. So when you're looking at the moon, you're seeing it the way it was maybe 1 second or a little bit longer in the past. While when you're looking at the sun, you're seeing it when it was 500 seconds in the past. So if we kind of take Pluto to be, Pluto's orbit to be the size of the solar system roughly, then that orbit is about 40 AUs, and it takes light 6 hours to travel from Pluto to the Earth. And the furthest we've sent anything are the 2 Voyager missions, which were launched in 1977. And the numbers I'm putting up here are from the 40th anniversary, which is 2017. So I haven't updated them because it's just easier to think about this in terms of 40 years. So in 40 years, Voyager traveled 140 AUs, or the light travel time is about 19 and a third hours. So it's barely gone that far away compared to the distance to Proxima Centauri from the sun. So it's gone maybe about 1% of that distance, and that's in 40 years. So it takes a very, very long time for even things like Voyager to cover distances like this. We're talking about thousands of years for it to get that far. So even to the nearest star, it's really, really far away. And we can go much, much further. So we live in the Milky Way Galaxy. And if you have a chance, you should both go out away from the city and away from city lights and try to look for this. It's very visible sometimes of the year. And this is a really nice picture. It's called the European Southern Observatory Milky Way picture. And if you go and search for ESO Galaxy or ESO Milky Way on the web, you can see this and you can blow it up and magnify it and look at it. It's our galaxy. It's a collection of stars that are held together by gravity, and they're also rotating. So if you've ever played with a frisbee or know what that is, that's sort of the shape of the galaxy. It's a disk, like a dinner plate. And except near the center of the dinner plate, it's bulged a little bit. And I'll come back and talk about that in a while. But the scale here is about 50 kiloparsecs. So it's a collection of maybe 150 or 200 billion stars. It's a very, very, very large object. And let's go and look at an older version of this with older telescopes. It's not as beautiful as the modern version. And the modern version, if you look at it on your computer, you can do a lot of things with it and look at it in different wavelengths and stuff. But probably this artist's drawing is the easiest thing to talk about. So it's about 50,000 parsecs. So if we want to turn that into how long it takes for light to travel, you multiply that by 3.25. And so you get about 160,000 years. So if you had something that traveled at the speed of light to go from this end to this end, it would take you 160,000 years. And you should kind of contrast that with the time it takes light to travel from the sun to the Earth, which is 500 seconds. And so that gives you some idea of the scale of this object. It's got maybe 150 billion stars, and it's arranged in a disk, and there's a bulge in the center. And the disk, it rotates in the plane of the disk. So the sun is about 1/3 of the way out from the center of the Milky Way Galaxy. It's about 8 kiloparsecs away. And the Milky Way Galaxy is surrounded by something called a halo, and that's probably about 10 times the size of the Milky Way. It's got a lot of stuff there, but we don't see most of it. And that's where the dark matter is thought to be a large part of it. There are these globular clusters, a few hundred of them that we're aware of. These are collections of maybe hundreds of thousands to millions of stars. And they're like spherical balls. They're held together by gravity, and they orbit the center of the Milky Way Galaxy. So this is a pretty huge object. It's our galaxy. We live in it. But there are many, many, many galaxies out there. This one is our nearest neighbor big galaxy, and you can also see this in the sky if you know how to look for it. And you can go look on the web at reputable sources like Wikipedia and try to learn where to look for these things if you're interested. This is also a spiral galaxy like the Milky Way. There's the central bulge and there's the disk. And you can see, I guess I wanted maybe should back up a little bit. You can see this black region over here. And this black stuff over here is not the absence of stars. I mean, there are an equal number of stars in this black pot as there are in the shiny pots up and below it. What this is dust. It's particles of small particles like silicates and other things that absorb the light of those stars, and it obscures them, and so you can't see them. And there are as many stars in the black region as there are in the shiny regions. You just can't see them because the dust is blocking them. And you can see the dust lanes in Andromeda also, because we're seeing the disk a little bit from above. Andromeda is a little bit bigger. It's about 60 kiloparsecs in diameter. And so if you multiply that by 3.25 years per parsec, it's about 200,000 years for something to cross this at the speed of light. I mean, you can't travel at the speed of light because you have a mass. And to travel at the speed of light, you have to be massless. Andromeda has satellite. These are galaxies, and they're also pretty big objects. They're two little dwarf galaxies. The Milky Way also has quite a few dwarf galaxies. You can't see any with your naked eye from the northern hemisphere, but if you go to the southern hemisphere, you can see two of them, the Large Magellanic and the Small Magellanic Clouds. So Andromeda is pretty far away from us. It's 750 kiloparsecs, or in terms of light travel time, it's about 2.5 million years from us. So when you look at Andromeda, that light that is coming through your lens, your eye lenses, and hitting the back of your retina and getting converted to electrical signals, that's been traveling in a straight line for 2.5 million years from whatever produced it in Andromeda, like whether it was a star or some hot gas or something. And it traveled in a straight line, and it came and hit the back of your retina, and you saw Andromeda. And this is kind of an interesting time in terms of human evolution also. So the oldest hominoid fossil that's been found is Lucy in Ethiopia, what is now Ethiopia, and she's about 3.25 million years old. So when this light left Andromeda, humans still were kind of not quite, we weren't quite Homo sapiens yet. So this is pretty far away in terms of time, but it's just one little galaxy. So these galaxies are held together by gravity. So maybe I can just back off and say a little bit more about this. So gravity is pulling all these stars in. And so clearly, if these galaxies are pretty old, there's something that still keeps this disk away from collapsing down to the center, because gravity is going to want to minimize the energy and pull everything in. And so what's happening is that the disk has angular momentum and it's rotating, and that's why it doesn't completely collapse down to the center. And even the central bulge, you would think it would collapse down to a much smaller region because of gravity. And the reason it doesn't do that is because the hundreds of millions or billions of stars in here, they all have velocities, and they're moving in different directions, unlike the dominant kind of velocity in the disk, which is rotational. So galaxies, there are two kinds of galaxies. I mean, they're somewhat similar to humans. They're galaxies that like to live by themselves, and then there are galaxies that like to be near other galaxies. And when you get galaxies close together, they start pulling on each other gravitationally, and they form a bigger object, which is called a cluster of galaxies. And we're looking at the center of the nearby Virgo cluster here. So each of these bits of light, even these tiny ones, they're all galaxies. They're not stars anymore. And each of these guys typically has 100 billion or 200 billion or 300 billion stars. And they're moving around each other because they have kinetic energy. And if they didn't have kinetic energy, they would all fall to the bottom of the potential well because gravity is going to pull them in. And they wouldn't be distributed across space in such a large region. So we're looking at the central region of the Virgo cluster. And the scale here is a few megaparsecs. That's a million parsecs. And so if you want to convert that to light travel time, you multiply that by 3.25. And so you'd get maybe 10 million years. So to cross this at the speed of light, it'll take about 10 million years. And this is only the center of the Virgo cluster. And the distance the Virgo cluster is from us is 20 million parsecs. So that's maybe 70 million years in light travel time. So Andromeda was maybe 2.5 million years away from us. Virgo is maybe 70, 80 million years away from us. So we're going out further and further. And a couple of these galaxies are kind of special. They are sitting near the center of the potential well. And just like when you think about satellites in orbit around the Earth has an atmosphere. So if your satellite comes down a little bit too low, there's going to be air drag on it. And it's going to be slowed down and it's going to lose its kinetic energy. And so it's going to want to drop a little bit in the potential well, and it'll come closer and closer in. And these guys, because they're in the center of the potential well, and they also have an atmosphere that's still made up of stars, and they kind of go out some distance away from the center. If a nearby galaxy comes near it, it's going to spiral in also. And these guys are called cluster dominant or CD galaxies. They have maybe 500 billion stars, and they're basically cannibals. They've eaten other galaxies that come too close to them. And so they're very, very, very heavy. But because they're sitting in this potential well, they don't spread out a huge distance in space, even though they're much heavier than the other galaxies you can see, because they're very compact. So this is what a cluster of galaxies looks like. We can go out even further and look at a whole collection across the sky. So let me just back up a little bit to this picture here. So we're over here 1/3 of the way from the center of the galaxy, and there's all this dust here. And this dust blocks light coming to us. So the way we can see better out of our galaxy is to look up to what's known as the North Galactic Pole. So you set up a coordinate system in spherical polar coordinates. This is the polar axis here, and the azimuthal axis, azimuthal angle goes around here. So if you want to see out, it's really somewhat easier to look at this region of space. And that's what this next picture is. It's a picture of that region of space. We're looking out. And this was taken at telescopes at the Lick Observatory, which is near San Jose, in the mountains near San Jose, which is in the San Francisco Bay Area. And this was taken in the late 50s and early 60s by these two astronomers. And at that point, there were no CCDs. There was hardly any electronics. And so they would take these glass plates and put emulsion on it and set it at the focus of the telescope. And then they would develop these glass plates. And then by hand, they would look at the glass plates and figure out which things were galaxies and what their positions were. And they figured out the positions. What you're seeing here is 400,000 galaxies, and they did this by hand. There were no computers that they could use and no laser scanners at that point. So the scale here is about 300 megaparsecs, or if you want that in light travel times, it's 1 billion light years. So if you traveled at the speed of light, it would take you 1 billion years to cross this. And there's a lot of structure in this map. So you can see this cluster here. This is almost directly at the North Galactic Pole above us in the Milky Way. And that's the Coma cluster of galaxies. So it's a pretty big cluster. It's probably got 5,000-6,000 galaxies in it. And each of those galaxies has maybe 100 billion stars on average. So it's a huge object. And you can see other clusters all over the place that are comparable to Coma. You can also see regions that are much darker. And these regions are dark not because there's dust in them. The dust does not spread out on these really large scales. It's kind of pulled in by the galaxies. But they're dark because they don't have a lot of bright galaxies in them. And they're called voids. And you can also see one-dimensional structures like this and like this and like this. And these guys are called the filaments. So there's three kinds of things. There's the clusters of galaxies, they're the voids, and they're the filaments. And one way to think about this is if you fill up your basin and you put some soap in it and make bubbles, then the voids are the central regions inside the bubbles, and there are no very bright galaxies in the voids. The galaxies tend to be distributed on the surface of the bubbles, and where two bubbles intersect, you can get filaments because the galaxies the galaxy distribution is enhanced a little bit because there's galaxies on one bubble wall with the galaxies on another bubble wall and stands out. And if you think about those filaments and how the bubbles drain, the filaments kind of drain towards the center. So you can see this guy drains towards Coma, this drains towards Coma, this drains towards Coma. And so the really bright clusters of galaxies are where some of the filaments come together. So this tells you something about the structure of matter distributed on a scale of a billion light years. So there are regions that look very, very different. If you looked over here, you'd see a big bright cluster of galaxies. If you looked over here, you'd see nothing. So a distribution like this is said to be anisotropic. So if you kind of think about what isotropy means, that means if you're standing at one point and you're looking in different directions around you, to your right and to your left and in front of you and behind you and above you and below you, if you see everything the same in all those directions, that's said to be an isotropic distribution of matter around you. If it looks very different in those different directions, it's anisotropic. And where you are now and the distances to which you can see, everything looks anisotropic. I mean, you could go up a little bit above Bangladesh. If you can get up maybe 1,000 feet or something and look to the south, you'll see the Bay of Bengal there. And if you look to the north, you'll see the Himalayas. And you look in the east and the west, you see different things. So the surface of the Earth is very, very anisotropic. And the same thing's true of our solar system. If you look in one direction, you see this big star, nearby star, the sun. You look in other directions, you don't see anything like that. And the same's true on the scale of the Milky Way. So if you look in from the sun towards the central region, you'll see the bulge. If you look outwards, you'll see much fewer stars. And even on the scale of a billion light years, things look very anisotropic. You look over here, you see void. You look over here, you'll see a cluster. The interesting thing that happens is when you go out to a scale of maybe 15 times bigger to 4,000 or 5,000 megaparsecs, that completely changes. And so what we're looking at here is what the Planck Satellite measured. So this is the European Space Agency satellite that was sent up with microwave detectors on it. And microwave radiation is part of the electromagnetic spectrum. It's typically got a wavelength of millimeters or so. And some of you probably have seen microwave ovens to cook stuff, and that's the same kind of, roughly the same kind of wavelength. So what this satellite did is it took a microwave telescope and detector up, and it looked around it in all directions. So if you think of yourself inside of, say, a football, and you're looking out in all directions, if you have the center and you can measure the temperature on the surface of the interior of that football, that's what we're seeing here, except instead of showing you this from the interior of the football, I've sliced the football from the North Pole to the South Pole and opened it up and spread it across here. And we do something very similar when we look at the globe of the Earth and we want to show it on a flat plane. You cut it from the North Pole to the South Pole and you spread it out. So if you want to put this back together, you have to identify this edge with this edge and close it up into a shell. So what we're looking at here is the light from photons that came to us from was the early Big Bang, when the temperature cooled down enough so that the photons could escape from the electrons and protons. And if we have time, we'll talk more about that. But that happened when the universe was maybe 380,000 years old. The universe now is about 13.75 billion years old. And so we're looking at the temperature of these photons because you can convert, you get the frequency, and then you can get the energy from Planck's relation that says h nu is the energy. And then you can use Boltzmann's relation, which is Boltzmann's constant, and the temperature is equal to the energy to get the temperature. And so we're looking at cold photons, colder than average photons and hotter than average photons that are coming to the Planck satellite from all these different directions in the sky. And one thing you might be interested in is the total average temperature as you average it across the whole sky. And if you do that, it's about 2.7 Kelvin, or maybe 2.75, 2.76 Kelvin. So that's an extremely, extremely low temperature. So room temperature on the Kelvin scale is roughly 300 Kelvin. So these are very, very cold photons. The other interesting thing you can do is you can compare the hot spots to the cold spots. And the difference in the temperature of the hot spots and the cold spots is 30 microkelvin, where micro is a millionth of a Kelvin. So the bumpiness is the difference in temperature between the hot and cold spots is 30 microkelvin. The average temperature is about 3 Kelvin. So you can divide 30 microkelvin by 3 Kelvin to get a delta T over T. And that's about 1 part in 10 to the 5, or 0.001%. So when you look over here, and you look over here, and you look over here, and you look over here, the difference is 1 part in 10 to the 5, or it's 0.001%. And if you go to smaller scales, you get much, much larger differences. You look over here, you see thousands of galaxies. You look over here, you see hardly any galaxies. And the differences become much, much more pronounced on smaller scales. But as you go to larger scales, the differences become very less pronounced. The universe becomes much more isotropic. So these are two very, very, very important facts about the universe. When you look locally on smaller scales, and you look at either the matter or the radiation, you find it's anisotropic in space. It looks different in different directions. When you get out to much larger scales and you do a statistical averaging, then you find that the matter and the radiation is isotropic on these scales. And I'm not going to really talk about how these facts came about, but if you're interested, you can study what's known as the inflation model of the early universe. And again, you should only look at very reputable websites like Scientific American or Discover, or usually Wikipedia is pretty reasonable, but you have to be a little bit careful when you use the web because you get a lot of wrong information there. So these are two really important facts. Now we want to move on to something that's even stranger, and that's that the universe expands. And this is a very, very difficult thing to appreciate. So let's try to talk about this a little bit. And it's kind of useful to think about what we mean when we're saying something is expanding. So when we say something is expanding, that implies we've got a measuring device that is not also expanding the same way. Because if we had a measuring device that was expanding as the universe expanded, you'd never notice the expansion. So it's kind of important to think about what's going on with your measuring device also. So let's take a very, very simple measuring device. Let's take a meter stick and think about what's happening. So in a meter stick, we have atoms or molecules, and it's kind of easier to think about it in terms of molecules, for instance, in terms of atoms, or we can think about any structure on the scale of humans. Like, the important thing is that it's all made up of atoms, and atoms have a nucleus that has positive charge, and they have an electron cloud that has negative charge. And if you're only interested in things on the scale of atoms and larger, you don't have to worry about the other two forces, the weak nuclear force and the strong nuclear force. The only things you need to worry about are electromagnetism and gravitational force. So if we think a little bit about what electromagnetism does, there's negative charges like electrons and there are positive charges like protons. And we know that electromagnetism repels electrons. So if you bring two electrons together, they get pushed apart by the electromagnetic repulsion. And if you bring two protons together, they get pushed apart by electromagnetic repulsion. So like charges are pushed apart. But if you bring a proton and electron together, they get pulled together. So unlike charges, get attracted. And if we kind of think again about what gravity does, so gravity just pulls stuff together. It does not have any repulsive component. So if you have two protons, gravity is going to pull them together, while electromagnetism is going to push them apart. And you're probably aware that the Coulomb force between the two protons is an inverse square law force, and that's pushing them apart. And Newton's gravitational force is also an inverse square law force, and that's pulling them together. So if you haven't already done this, you can take the system and compute the ratio of the electromagnetic force that's pushing them apart to the gravitational force that's pulling them together. And if you do this, you'll find that the electromagnetic force that's pushing them apart is much, much, much stronger. And because you have both these inverse square laws, the R squareds cancel out, and you don't have to do this at a specific distance. This is true at all distances. So electromagnetism is much, much stronger, and gravity is very, very weak. So if you kind of think about what humans are like, humans are made up of atoms. And so if you're sitting next to somebody now, you're not really exerting an electromagnetic force on that person, because your electrons are going to be pushing that person's electrons away, and your protons are going to be pushing that person's protons away, but your electrons are going to be attracted to that person's protons and pulling them towards you. And the same is true for your protons and their electrons. So overall, because you're charge neutral, there is no electromagnetic attraction between you and your neighbor. I mean, unless, of course, you combed your hair very, very vigorously before you came to this talk. And if you did that, you built up some static electricity on you because you've broken down some of the atoms. But that's kind of the unusual situation. So on human scales, you don't attract your neighbor or repel your neighbor through the electromagnetic force, but you do attract your neighbor gravitationally. And that gravitational force is proportional to your mass and your neighbor's mass. And if you kind of scale this up to much, much larger objects like stars, those stars are also roughly neutral electromagnetically, so they don't affect each other through the electromagnetic force, but their masses are much, much bigger, and so they exert a much stronger gravitational force on each other. So as you go from smaller scale objects to larger scale objects, the physics changes because you go from objects that are charged to objects that are neutral, because electromagnetism gets screened on in bulk objects because it's mostly made up of atoms and molecules and there's no unbalanced charge. But on small scales, there is unbalanced charge, and there's also interactions on much, much smaller scales that are important. So if we kind of think about what an atom is, so an atom has this very, very heavy central object, the nucleus, and then on a scale of a factor of maybe 10 to the 4 or so bigger, on a length scale of 10 to the 4 or so bigger, it's surrounded by this electron cloud. But everything inside that atom is just empty space. So you're made up of atoms and molecules, and you're basically empty space. And the chair you're sitting on is also basically empty space. So you might want to be thinking about why you can't just fall through the chair or why you can't walk through walls, because it's all empty space. And the way you can't do this, the reason you can't do this is because if you think about the structure of matter, you have electrons, these electron shells, and the atoms are close to each other and the electrons are pushing against each other. And so if you have two neighboring atoms, they're going to be pushing each other apart, but then you go over to the next set of atoms, they're also pushing each other apart. And so they get to be very, very rigid because those electrons are pushing each other apart. And so that's where the structure of matter comes from. It's the electromagnetic repulsion between electrons. And even though you're mostly empty space, you can't walk through a wall because your electrons in your atoms are going to be pushed away from the electrons of the atoms in the wall. And that's what gives matter structure. That's what holds your meter stick together. And on the scale of the meter stick, the gravitational force is extremely weak, so it's not going to do anything to it. But when you get to very, very, very large scales, the gravitational force completely dominates over the electromagnetic force. And so we have to use the best model of gravity to describe what's going on very large scales. And that model of gravity is Einstein's theory of general relativity, which is really difficult to appreciate. And it only holds on this effect that I'm talking about only applies on very, very large scales. I mean, we are affected by Einstein's theory of general relativity every day in our life. And if you use your GPS on your smartphone, that's correcting for even general relativistic effects and as well as special relativistic effects in the satellite system and the electromagnetic signals there. But we're interested in what's happening on very, very large scales. So Newton came up with his very accurate description of mechanics on small scales, and he made a number of assumptions. So one assumption he made was that everything everything happens in this uniform time. And when you collide two balls, there's some kind of external clock, and that runs uniformly, and it gives you the time. And he also said space was kind of fixed. And Einstein realized that he could give a more accurate description of reality if he allowed both space and time to change and participate in the dynamics of physics. And so what happens is that general relativity kind of looks around in the universe, and it looks in these regions where there's less mass, there's fewer heavy objects, and it creates more space there. And that space has to go somewhere, and it spreads out, and everything lives in that space. And as the space is spreading out, that's the expansion of the universe. And this is a very, very difficult thing to appreciate, and you need to think about it quite a bit. So I'm going to try to demonstrate a couple of things here. So I have this elastic band here, and I put a wave on it. And you can see the peaks and troughs of this wave, and you could take your meter stick and you could measure the wavelength. And now I'm going to expand the universe. And if I expand the universe, you can see that the wavelength increases. If I contract the universe, the wavelength decreases. That's because this wave is fixed in the space and you're making the space expand and contract. So this analog is not terribly accurate. I mean, it tells you what's happening to the wavelength, but I'm holding it at the ends. There are no ends to the universe in most cases. And it's not that gravity is pulling on the universe. Gravity is going into the universe. General relativity is going into regions in the universe in space, and it's creating more space and it's pushing stuff out. And this is not happening just in one dimension. It happens in all three spatial dimensions. So this is a cartoon of the same kind of demonstration. It's kind of a little bit difficult to do these over video, but here's what I have. So we have a wave, and it's got a wavelength, an original wavelength, which we're going to call lambda naught. And I'm going to call the size of the universe the distance between the fingers here. And as time goes on, the universe is expanding, and the wavelength gets stretched, and the size of the universe gets stretched. And we need to have something that characterizes the size of the universe. And what the astronomers and cosmologists do is they call that the scale factor. Excuse me. And the symbol for that is A. And the scale factor is a function of time. So as time goes on, this gets bigger and bigger. And you can see, if you think about this, that the wavelength gets bigger and bigger in proportion to the scale factor. It's not that difficult to think about it. You can actually do this. You take an elastic band, draw a wavelength on it, draw a wave on it, and measure it with your meter stick. So astronomers don't like talking about scale factors. They prefer talking about what they call the redshift. And that's this Z here. And this is defined as 1 plus Z is equal to the value of the scale factor at now compared to the value of the scale factor when that light was emitted. So you emit light from some star in the past, and it starts spreading out as time goes on, and the wavelength starts stretching. And so the scale factor now could be this distance, and the scale factor when that light was emitted could be this distance. And you take this ratio and you get the redshift. And the thing about the redshift is as you go back in the past, the scale factor gets smaller and it's in the denominator, so the redshift gets larger. At the present time, A is equal to A now, so this is equal to 1, and the redshift Z is equal to 0. But as you go back in time, the redshift gets larger and larger. And this was the guy who kind of first discovered this expansion of the universe, but he didn't really realize what he had discovered. So we can kind of think about, well, I guess you could kind of think of this a little bit more carefully. The expansion happens in all dimensions, all space dimensions. So it's not a firecracker, an explosion going off at one point in space at one instant of time and everything spreading out. But it's each point in space that's moving away from every other point in space. And so if you kind of look at this again and look at any 2 points, each point moves away from every other point. So Slipher, in 1912, he was using this telescope and he was looking at galaxies some distance away outside the Milky Way. And he looked at spectral lines of light that he was catching through this telescope. He put it through a diffraction grating and broke it up into its spectrum. And he saw that these objects had wavelength ratios between their lines that were that allowed him to identify what elements were emitting this light. And then he went and took those same elements and he heated them up in his lab, and he measured the wavelengths there. And he realized that the wavelengths that he was measuring in his lab were different than the wavelengths that these elements had when he caught the light through the telescope. And they were longer wavelengths when they came from through the telescope, and they were longer than the ones he could measure in his lab. So he was seeing the Doppler effect. So if you think about a police car with a siren or an ambulance with a siren, if you are standing there and it comes towards you, then the pitch goes up, and as it goes away from you, the pitch goes down, and that's just the Doppler effect. And light does the same thing. It's a little more complicated for light because you have a moving source and you have to do time dilation also. For sound, the speeds involved are not relativistic, and so you don't have to worry about the time dilation effect. But I'm sure you're all familiar with the Doppler effect for sound. And so Slipher was seeing that these wavelengths were larger than he expected, and he said these sources have to be moving away from me. And it could be that there was a big explosion near him, and all these galaxies originally were near him and they moved away, but that's not what's happening. And I'm trying to show a cartoon here to illustrate that effect. And this is a bread, and there's yeast in it, and there's chocolate chip cookies put in here. And this is it at one instant of time, and this is it in a later instant of time. And if the yeast rises, then the bread is going to expand. And this is just a part of my imagined universe. It can't be a finite, it can't just be this part, because if it was, you could go to the edge and you look out and it will look different than it would look when you were looking inside, and that wouldn't be isotropic. And I argued that the matter distribution is isotropic. So in a flat universe like this, you've got to go out to infinity in all three dimensions. So if we ask what an observer does sees on any of these chocolate chip cookies, we put her on chocolate chip cookie 2 and ask her what she sees. She'll tell you she sees 1 and 3 and 4 and 5 and 6 move away from her. And you put an observer on chocolate chip cookie 4 and you ask him what he sees, he's going to tell you all of them move apart from each other. And I've got another analog demonstration here. So I've got an elastic band with ping pong balls, if I can unknot it. And these ping pong balls are my galaxies. They do not expand with the universe. They're like the chocolate chips. What's happening is that the space between the galaxies is increasing because general relativity is creating more and more space. And this is just the expansion of the universe. So here we have a three-dimensional universe instead of the one-dimensional one I'm showing you over here. And so there's going to be an expansion in the vertical and in the two horizontal things. And if you think about how these volumes are related, the volumes will expand in proportion to the cube of the scale factor, because each linear dimension expands in proportion to the scale factor. And this is just Hubble's law. So after Slipher in 1912, Hubble had access to a much bigger telescope, and he could actually see these stars in these galaxies that Slipher was looking at. I mean, Slipher could not see the individual stars because his telescope was pretty small. And Hubble could use his bigger telescope and he could resolve these stars. And he saw that some of them were pulsating stars. And these stars were known as Cepheid variable stars. And they are very, very useful stars because of a relation that Henrietta Leavitt had discovered, I think in 1906 or 1907. So Henrietta Leavitt was an observer. Well, she wasn't really an observer. She was at the Harvard-Smithsonian Center in Boston. And these astronomers who would take these photographs on glass plates would send all of these plates there. And they had a huge collection of them. And the astronomers would often rephotograph the same region of space over and over again. And Henrietta Leavitt would look at these plates, and she'd realize that there were pulsating stars in these plates. So maybe in March of some year, she saw the same plate, and there was a region there that was very, very bright. And in June of that year, the next plate, that region was dim. And so she identified these pulsating stars. And because she had photographs of many, many, many different times for the same region, she could measure the period of the pulsation. And she realized that from these pulsation periods, she could figure out how intrinsically bright these stars were. She could figure out the wattage of the stars, because she found nearby stars that did the same thing close to the Earth, and that she could measure the distance to these nearby stars using trigonometry, just measuring the position, the angle to those stars from two different positions on the Earth. And then you look at the triangle, and then you can get the distance between the Earth and the star. And so once you get that distance, and you know that the light from the star, the intensity of that light is going to obey the inverse square law, you can measure the amount of light you get on the surface of the Earth from that star, and then you can figure out the wattage of the star. So she had the wattage of these nearby stars. She could measure the pulsation, and she found that there was a good correlation between the wattage and the pulsation period. And so that once you get the pulsation period, you could figure out the wattage of the star. So Hubble knew this relation, and he did not know how far these galaxies were from him, but he could measure the pulsation period. And then from that pulsation period, he could get the wattage of the star. And then from the wattage of the star, he could use the inverse square law, and he could get the distance. So he measured the distances to these stars, while Slipher used Doppler's formula, and he measured how fast the galaxies were moving away. And then Hubble and Humason discovered this very, very simple relation between the distance to the galaxy and the speed of recession of the galaxy. And it's a linear relation. So if the galaxy was twice as far away from us, the speed of recession would be double. If it was 3 times as far away, the speed would triple. And the constant of proportionality is called the Hubble constant. And in the astronomers' units, it's about 68. And it's a little strange that the astronomers use these units, but unfortunately they do. They measure the speed in kilometers per second, and they measure the distance not in kilometers, because if they measured it in kilometers, the unit of the Hubble constant would be inverse seconds, but they measure it in megaparsecs. So the units of the Hubble constant are kilometers per second per megaparsec. And that's become the tradition. So the Hubble constant is just something that has dimensions of inverse time, and the inverse of it gives you a rough idea of the age of the universe. But this is the Hubble law, and you can see it here. It's pretty well established now. On this axis, I'm plotting the velocity of recession of the stars. On this axis, it's the distance to the star. So you can go down here. We can ignore this. These are the residuals. So if you go to a star that's a galaxy that's 100 megaparsecs from us, you find that it's receding at about 7,000 kilometers a second. And you go to a galaxy that's 200 megaparsecs from us, it's receding at about 14,000 kilometers per second, and so on. And this straight line is the best fit. This is the slope at 72. This is older data. My favorite value now is about 68. And this is the expansion of the universe. So I'm not sure whether I should just stop here and have time for questions, or whether you want me to continue.
So I think you can continue. We have got a few questions, so we
Okay.
can discuss later.
Okay. So the expansion, the universe is expanding, and so we have to be really careful about what observers we use when we're talking about observations, because if you have an observer moving with respect to the expansion, it will not look isotropic because you'll have the Doppler effect. So if you had a rocket and you're going in a rocket, the light in front of you and the light behind you would be a slightly different wavelengths than the light to your left and right if you're in a uniform radiation bath. So we have to look at observers that are at rest with respect to the expansion. And these observers are called cosmological observers. So if you kind of think about this a little bit and think about yourself on the Milky Way, and you have friends on other galaxies, if it's possible to think about that, at least it's possible to think about that in your imagination. So you have a friend on the Andromeda galaxy and you ask her what the universe looks around her on very large scales. She's probably going to tell you that it looks roughly the same as what it looks around you, that it looks isotropic around her on very large scales. And there's a theorem then in geometry that tells you if you have two observers that are separated in space, so you've translated yourself in space, you've gone here and you walked to Andromeda, if it's possible to think about doing that, and then you look around and it looks roughly the same on Andromeda, then this theorem in geometry tells you that you're actually in a much, much more symmetric distribution than you are in a purely isotropic distribution about one point around you, centered around you. So the simplest example of such a homogeneous distribution is homogenized milk. So if you kind of think about a pouch of milk or a bottle of milk, and you shrink yourself down small enough, and you put on a scuba suit and you start swimming around in that milk, it'll look exactly the same whiteness to you no matter where you are, provided you don't get to the edges of the container. So that distribution has much, much more symmetry than a distribution that's just isotropic about you at one point. So if we assume this cosmological principle, and this is a generalization from what Copernicus assumed, he said there's no reason to think that because we live on the Earth that it's going to be the center of the solar system. And Einstein took this one step further in his first paper in cosmology, that we aren't in a preferred position to observe the universe just because we can see it, and that any other position in the universe, any other space point is an equally good position. So if you have a spatially homogeneous distribution and you take the simplest topology, then there are only three possibilities for the spatial geometry of the universe. And these are the flat and the closed and the open universes. Okay, so I cannot show you the three-dimensional geometries because they're too difficult to draw and look at. So what I've done here is I've shrunk down one of the spatial dimensions to 0 size, and I'm going to just look at two-dimensional analogs. So instead of just thinking about this as a plane, we're really in a three-dimensional Euclidean space, and so you have to keep that in mind. So we could be living in a space such as the surface of a sphere, and we have to think of ourselves as ants that are restricted to the surface. So all we can do is we can walk on it. There's nothing inside. We cannot go into it. There's nothing outside. And as time goes on, if we pick the expanding solution of Einstein's general relativity, the sphere gets bigger and bigger, and the distances between the grid points gets bigger and bigger, and that's the expansion of the universe. And this is called a closed universe, and it has positive spatial curvature. So the easiest way to think about the scale factor is to think of it in this case as the radius of the universe, and as time goes on, this gets bigger and bigger, and the surface gets bigger and bigger. So this is a compact geometry. It has no edges. If we go to the flat case, like the top of a table, and we go out over here, if we look out, it's going to look different than if we look in. So this cannot be a flat universe. So if you want a flat universe, you've got to go out to infinity in both dimensions. and you cannot have just a little patch that's flat. So this is an infinite universe, unlike this case, which is a compact universe, because the surface of the sphere has no edges. This has to go out to infinity in both dimensions, and it expands. And you have to think of the expansion as the grid points getting further and further apart. So you have an infinite number of grid points here, so you have an infinite space, and it's going to keep expanding. And finally, you have the open universe. So this has zero curvature, this has positive curvature, this has negative curvature, and it also goes out to infinity. It's like a saddle, and if it didn't go out to infinity, you could go to the edge, and the edge would look different when you look out and look in. So we have this parameter here, omega, and I'll explain this in a minute. For the flat case, omega naught is equal to 1. For the closed case, omega naught is greater than 1. It's an overdense universe. And for the open case, omega naught is less than 1. It's an underdense universe. And I don't know if I should stop here and let's answer questions. Do you still want me to continue?
I think so. We can discuss about the question.
Okay, so should I get out of this?
Yes, you can stop share.
Okay.
Okay, I can add the question in the screen. I think you can also see those questions.
Okay, so they're going to be in the chat or
in the comment section. I can add the question in the screen. I think you can also see this question.
Okay.
The first question: how do we determine the light falling on the Earth from nearby galaxy is some million years old?
Okay, so we know the distance to these nearby galaxies, so we can measure them through various techniques. So if you think about how you measure the distance to even say the moon, so one way to measure the distance to the moon is to go to 2 points on the surface of the Earth. Say you go to Dhaka and you go to Delhi, and you look at the moon with a telescope, and you measure the orientation of that telescope with respect to the vertical at the position where you are. You can measure the angle relative to the vertical at Dhaka and at Delhi. So you have this triangle with one vertex at the moon and the two other vertices at Dhaka and at Delhi. So you can measure the two interior angles of that triangle, and you can measure, because you know it adds up to 180 degrees, you can measure the third angle. And then you measure the distance between Dhaka and Delhi. So you have one length and you have the two angles. And so you can figure the distance between Dhaka and the moon. And so you can do this on larger and larger scales. So clearly it's very difficult to measure angles. And so you want to try to get as big an angle as possible. So maybe you go at one time of the year at Dhaka and then go again and do the experiment 6 months later when Dhaka is on the other side of the sun from its original position. So your baseline then is 2 AUs. And if you have a tiny angle, you can get that triangle and measure the distance. So you can measure the distance to Andromeda, and that distance is 750 kiloparsecs. And you know that it's mostly vacuum between Andromeda and Earth. And you know the speed of light in vacuum, it's 3 times 10 to the 8 meters per second. You know the distance. And so you can divide the distance by the speed, and then you'll get the time. And so it takes light 2.5 million years to travel from Andromeda to Earth. And that's how we know that we're seeing Andromeda as it was 2.5 million years ago.
Okay, sir. Thank you. We have another question. So, do string theory represent one of the most promising approaches for a consistent theory of quantum gravity and matter, solving the mystery of dark energy and dark matter?
Okay, so I'll separate that into 2 parts. So this is the first part, whether it's a promising approach to quantum gravity. And it is a really promising approach to quantum gravity, but we don't really know whether it's going to work. So the really interesting thing about string theory is that it's consistent with quantum mechanics. You use quantum mechanics to describe it. And when you analyze string theory, you find that it includes gravitational perturbations or gravitons. Um, it's kind of unclear whether there's a solution of string theory that describes the real world as we know it, because the mathematics of string theory is very, very difficult, and we do not know how to solve the equations of motion. And we do not know at present whether it can describe like even the standard model of particle physics, like the Glashow-Salam-Weinberg model and QCD. So maybe in the future, we'll be able to see that it actually describes reality. But right now, it's a consistent quantum mechanical description of a system that includes gravity, and it's the only one we have. So it's really interesting mathematics. I don't know if it's going to work for physics at this point.
Sir, thank you. We have another question. Can neutrinos' tiny mass be linked with the accelerating universe expansion?
So that's a very interesting question. So if you look at the cosmological constant, which we seem to need if we're going to explain the accelerated expansion, that has some energy density. So if you think about this in natural units, well, so an energy density, you can multiply it by, divide by c squared, and you'll get a mass density. And so that's grams per centimeter cubed. And in natural units, that has units of 1 over distance to the fourth, or its energy to the fourth power. So if you take the fourth root of the energy density of the cosmological constant, you get an energy scale, and that's a few millielectron volts. So that's the scale that we need from some place to explain the accelerated expansion of the universe. And it's not that far away from the neutrino mass scale. And so people have thought about trying to use the neutrino mass scale to explain the cosmological constant, but I'm not aware of any model that works. I mean, there's been a lot of discussion of trying to get a model like that to work, and people are working on that now.
Thank you. This may be the last question. So I have few questions. If the universe is expanding, then can we measure the rate of the expansion? Two, is the getting diluted? And third, how many energy conversation law is followed here?
Okay, so the energy. Okay, let's just start with the measuring the expansion rate. So we can measure the expansion rate. So the expansion rate is just the Hubble constant now, because that's telling you the expansion rate. It's got units of 1 over time. And if you go back and look at galaxies that are further away, they're further back in the past when you're seeing them, because the light takes that time to reach us. So you can measure Hubble's law back in the past and compare Hubble's law then to Hubble's law now. And we find that the expansion of the universe is accelerating, and we can measure it pretty precisely. And we can measure it back to the past through using a whole bunch of different techniques. So we can see that the expansion rate is accelerating now, and the universe is about 13.75 billion years old. And so when you go back to when it was about 4 or 5 billion years old, we can see that it was decelerating, and we can go back even further and measure the expansion rate there. So the expansion rate can be measured. It was decelerating in the past. It's expanding now. And as things get spread out, everything gets diluted. So you have any volume you're focusing on, it gets bigger and bigger. And so your density is mass per unit volume. So if you're just talking about mass densities, The mass does not depend on the expansion of the universe, but the volume does, and the volume's in the denominator. So everything's getting more and more dilute. And you have to think about what is contributing to the expansion and how you add up the total energy. So if you're just focusing on the energy of stuff in some volume, that's decreasing, but space is also getting bigger and bigger, and so the gravitational field is also involved, and so that's soaking up this energy. That's where it's coming from. And so the total energy, when you add up everything all in the universe, is actually equal to zero. And it's getting changed between the energy in the gravitational field and the energy in the matter part. And that's why people are really interested in trying to create a universe, because you're actually almost certainly creating something that's total zero energy. And so you can kind of think about doing this quantum mechanically at very, very early times. And that's one way people have tried to figure out how to nucleate an inflationary universe, because you don't have to create any energy, because the total energy is zero, and it's just the distribution between the gravitational field and the matter part that's changing as a function of time as the universe expands.
Okay, sir. Thank you for your wonderful presentation and discussion session, sir.
Thank
So
you.
we can conclude, as we don't have any question. So I'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for giving us this opportunity, sir. So it's
Thank
a
you
great
very
opportunity
much
for
for
a student
inviting
and the
me.
viewers. Yeah. So
Yeah.
hopefully in near future we can arrange a face-to-face session, as if the situation become better.
Okay,
So
great.
bye
And
for
yeah,
today,
I'll be
sir.
happy to do this again.
Thank you,
Thank
sir.
you very much, and have a
Thank
great
you.
evening.
Bye
Okay.
bye.